All right, folks, here we go. Young's double slit experiment part 2. So, what do I have here? Well, this is the slide that I have that I brought home, which is not my double slit, right? In fact, you can't even see any slits. Well, why is that? Well, this device is something known as a diffraction grating, Grating. And essentially what this is it is billions of slits that are really close together, which is why it looks transparent, but it's not actually. You remember in the video that guy had a slide where the slits were separated by 0.25 millimeters, 0.5 millimeters, 0.75 millimeters, and 1 millimeter. These slits are so close together that there are 10,000ths of a millimeter in between the slits, right? So they're really, really, really close together, and there are a lot of them. And so it's that's what this device is. So we're going to see the impact of this device on the experiment. So I have my normal laser pointer here. Boom. That creates a red dot. So I'm going to shine the laser light through the diffraction grating. Let me get it to a place where it's going to be stable. Okay. And we can see what then occurs over there. Boom. There it is. We can see exactly what the guy saw before, except notice here, what's true is that I have another laser so I can point things out. This line here, which is the principal maximum, is directly across from where the laser would have hit if there was no diffraction grating or double slit there. And then these are our first order maximums. Those are on the A1 antinodal lines. Okay? And then we're going to call this distance here and that distance there x. So x is going to be defined as the separation distance between adjacent antinodal lines, or the separation distance between adjacent maxima. Now I keep calling these antinodal lines. We're not seeing lines, right? We're only seeing where those light rays intersect the wall. So let me show you that they are lines. So bear with me a second here as I go over, turn off the light, go over here, okay? And what I'm going to have to do here is clap an eraser. So I'm going to put the phone down for a second, clap the eraser, and then pick it up back up quick so you can see. Oh, there they are. So pretty, right? The actual antinodal lines were that Tyndall effect that we looked at before. And so you can see then that really what's happening here is if I move my hand back and forth, right, we don't see where the light is until something intercepts it. So they're actually antinodal lines. I'm going to turn the lights back on so we can see some stuff. So a couple of things from there. Now notice here that these antinodal lines are a lot more spaced out than the ones in the video we watched. That must mean that x is a function of something that's different between his experiment and my experiment. I'll tell you, the laser light that we're using is identical, right? It's that red laser light. 686 nanometers is the wavelength of that red light, because that's what laser light puts out, something around that. But the only thing different here is the separation distance between the slits, because I'm using the diffraction grating and he was using an actual double slit. So my separation distance D was a lot smaller. Therefore, notice I get a lot larger X. So we're going to find out that that is a inverse relationship. The smaller the separation distance between slits is, the larger the spacing. So let's see, what else can I vary? Well, one thing I can vary here is how far the laser is from the wall. And you can see, or from the slits, that's not changing anything. The other thing I can vary is how close the slits are to the screen. I'm going to push the box forward, and you can see that X is getting smaller as the distance between the slits and the screen decreased. And we're going to find out that that is a direct relationship. The last thing that we can vary here, whoops, pull the box back, is I'm going to switch off to a different laser. I have this laser here, which can do a red, but it can also do a green. All right, so here we go. Watch where the red maxima are. Oops. Now green. Now green. What happened? Red, green. Hopefully you can see that the green are closer spaced. So let's talk about green light. What's true about green light compared to red light? Green light's frequency is larger, right? But what's smaller about green light? Oh, it's wavelength. So here, the lower the wavelength of light, the smaller the separation distance. So there you go. Beautiful. So that kind of explains something from the video. In the video, we saw white light being used, and that would mean that each color, each wavelength of white light was having its antinodal lines at different x's. When the x's were similar enough together, they pretty much were at the same spot to make white light, and when they were far enough apart, you saw them as separate colors. Okay, cool. One last thing for fun, just to show this. Oh, actually, hold on before I do that. Here we go. Right now, notice here that my pattern spreads out horizontally. These slits right now are oriented vertically. I'm going to now turn the device 90 degrees. You can see that the pattern now spreads out vertically because the slits are horizontal. Why do I bring that up? Because I want to show you these glasses, which are neat, right? These lenses are, ooh, pretty colors. We'll talk about that in a second, are diffraction gratings, but they're kind of special because watch, right? Shine the laser light into that, and let's see what we see over on the wall. What? Oh, these glasses have not only vertical slits, but horizontal slits. So we're seeing that pattern spread out both horizontally and vertically. And here I think you can see very beautifully that the maxima are evenly spaced, that the maxima get less intense as you go away from the central maximum. It's pretty neat. Now I do want to show you what happens with these glasses when I look at not monochromatic light, but polychromatic light, specifically white light. So this is going to be a little bright there. That's the light in my room. I'm going to put that lens in front of it. Okay. Oh, crazy. There you go. And so what I hope you can see is if we go from right to left from the center, in the center, we just see the bright white light because that's where all the light is coming from all the frequencies. But then if you look at that next dot over to the right, you can see violet on the left and red on the right and white in the center because there's still enough overlap of all the different colors to make some white light. But that shows that violet, which has a lower wavelength, doesn't spread as far. If you look then at the second order maximum, the A2 lines, those are really differentiated. You can see a clear purple dot and a clear red dot as well at the end, where the red dot is further out from the center than the purple dot is. So now if I just turn this, I'm going to do all sorts of neat things. And just to show you that this also works with sunlight, I'm just going to show you that it's a little bit more blurred because the light is so intense that even the white light is drowning out some of the colors, but that's what it looks like without the goggles. That's what it looks like with. Everyone paired these goggles just for fun, but there it is. And so the Young's double slit experiment, one of the most important experiments because it proves that light acts as a wave because you see those places of constructive and destructive interference. We have the dependencies. Now let's get some of this stuff in our notes.